The final investigation reports on the OceanGate Titan are out, and after 2 years of theories, 3 separate agencies have delivered the definitive verdict on what crushed it on its way down to the Titanic. And there's a lot that we didn't know here. The carbon fiber everyone blames, not exactly the villain. Well, we'll get to that. The implosion that shocked the world, it was set in motion a full year earlier on a dive that everyone walked away from. And the biggest warning sign was hiding in OceanGate's own data the entire time. Today, this is a pure engineering breakdown, a mishap investigation, how this sub was actually built, the exact chain of failures the investigators uncovered, and the one piece of data that gives us all away, and what this means for future Titanic-bound submersibles. I'm Ricky, and this is 2-Bit Da Vinci. This video is brought to you by Mammoth. We're doing this video because this is the final stage of an engineering investigation. After all the hard work, after the long hours, and all the reports are out, the final findings. Now, we're going to try to cover the most important things, but we'll put a link in the description to a document that I made that lists all of them with links so you can go check out the PDFs directly and dig deep and look at everything that these tests and reports concluded. Let's start with the carbon fiber. I've seen a lot of comments on a lot of OceanGate videos, and a lot of people point out the carbon fiber being a bad choice. But here's the thing. The Canadian board ran the actual numbers, and a properly built version of that exact hull should have been almost indestructible on the timescale that mattered for this investigation. It survived 13 trips to the Titanic and back. A clean version could have done that hundreds of times more without issue. So if the material itself could have worked, why are we talking about a debris field 3,800 meters down in the ocean? Looking at this can, the easiest way to crush this would be right here. This would be the point of the maximum deflection, right here in the middle, the furthest away from these support rings on the outside. So just like that, I can crush this. A sphere doesn't have that same weak point. Squeeze it from any angle and the stress spreads out evenly, which is exactly why James Cameron's Challenger and almost every serious deep sea sub puts people inside a sphere. So why did OceanGate choose a cylinder? Because a cylinder is the only way they could have fit 5 paying customers inside, then be able to have an open cabin where they can all be together. A sphere is amazing for pressure resistance, but it's horrible for packaging, right? It's why rooms aren't circular. Where would you put a bed? Where would you sit? This is not ideal for passenger comfort or occupancy. This is. Now, a cylinder isn't an automatic death sentence. Every military submarine is one, but it puts you on hard mode from the start because now the hull is fighting a load it's naturally weak against, and you'd better build it absolutely perfectly. They named it Titan, built the hull from carbon fiber, downgraded the titanium end caps from grade 5 to a cheaper grade 3, and pointed it at the Titanic. This was, to say the least, not built perfectly. Here's where it gets counterintuitive. Carbon fiber is incredible stuff. Bundles of carbon strands thinner than a human hair with a strength to weight ratio better than steel. The problem is fatigue, how material wears out over repeated stress cycles. Every dive loads the hull and unloads it like bending a paperclip back and forth. And unlike steel or titanium, carbon fiber can hide the damage deep inside where you can't see it. But the Canadian board calculated that a defect-free version of this hull would have used less than 0.00001% of its useful fatigue life across the 24 dives. It should have survived millions of trips of this variety. The as-built hull was a different animal. Using the weakest real sample they tested, that same hull may have burned through more than 82% of its fatigue life in those same 24 dives. And here's an interesting finding. The hull's safety factor in the circumferential direction, the hoop direction, the one that actually carries the crushing load, came out to just 1.11, below the 1.25 the design itself required. That means that they decided this is how much maximum load it would have to build it to withstand 1.25 times that, but it was only 1.11. So in the direction that mattered most, this hull was under strength the day it was delivered, which is why it did survive 13 trips and failed on the 14th. This is Mammoth, and instead of paying $20 a month for Gemini, ChatGPT, and Claude, Mammoth is a platform that gives you access to all the best models in one place, whether it's for text, images, videos, research, or reasoning. The interface is clean and familiar, but check this out. When I was researching this script, I used Perplexity. but I can easily reprompt my request and pick a new model, like Claude Opus 4.6, and compare the results side by side. For images, Nano Banana is really good, but I can easily compare to others like Stable Diffusion with the same prompt. Now, Mammoth even supports video models like VO3, Grok Video, and Sora for high-quality videos for your next project. Create custom Mammoths with unique system prompts for the things that you do most. I have a custom Mammoth for research and another for designing thumbnails. The user prompt is the part we type in chat. It's the what, but the system prompt is the why and how. It tells the AI how to act and think, like be my lead researcher or you are my chief software engineer. And now you can share your custom Mammoth, so create once and share with your friends or team. If you like command line AI tools, there's Mammoth Code that installs just like Codex or Cloud Code right in your terminal. And they even have API keys if you're building an AI-powered app. So level up your AI game, bringing the power of the latest and greatest models in one place using Mammoth AI, and get started today using my links in the description. Huge thanks to Mammoth and you. Now back to the show. So where did the defects come from? The manufacturing, and the details are rough. The 5-inch thick hull was built as 5 separate 1-inch thick layers of carbon fiber, stacked and glued one on top of the next. This means the innermost layer, the one that's facing the highest pressure, went into the oven and got cured 5 separate times, soaking up the heat stress with each cycle. Remember that layer because we'll get back to that. During the build, the carbon fiber developed wrinkles, places where the fibers buckle instead of lying flat, which is exactly where composites lose strength. OceanGate's fix, they ground the wrinkles down by hand. Investigators found as many as 12 ground down layers in a single sample, and grinding a wrinkle on one layer just pushed a new wrinkle into the layer above. The fix kind of propagates the problem. Then the voids. The tiny pockets of trapped air average around 2.7% of the volume. That bloated the wall so much that it no longer fit the titanium ring it slotted into. So they machined down the outside, shaving fibers off the very surface meant to carry the load.
It's pretty simple, but if we mess it up, there's not a lot of recovery.
And the voids weren't random. They clustered worst at 2 glue lines between layers 1 and 2 and layers 3 and 4. And here's the kicker. The hull was wrong from the blueprint. Boeing's own feasibility study had called for a 7-inch wall. OceanGate was 5. The design also quietly dropped the 45-degree plies, the diagonal layers that help laminates resist shear. And to this day, nobody at OceanGate could tell investigators why, and Boeing was never even consulted on the change. When the recovered material was tested, its through thickness shear strength swung between 6.92 and 12.05 KSI, thousands of pounds per square inch, nearly a 2-time spread within the same part. It was off-spec, underbuilt, and wildly inconsistent from the very first ply. Now, this is probably something you haven't heard much about because the data only came out in these final reports. Rewind to July 15th, 2022, almost a full year before the implosion. The Titan was finishing dive 80, coming back up from the Titanic when everyone aboard hears a loud bang. OceanGate logged it, chalked it up to the sub settling, and kept diving. The bang was the hull tearing itself apart on the inside. When investigators recovered the wreckage, they found the carbon fiber had completely delaminated, separated into sheets between layers 1 and 2 and between layers 3 and 4. The exact failure around that 5 times cured inner layer. And the glue between those layers was rubbed and worn, and debris ground into the gaps, physical proof that these sheets had been sliding against each other before the final dive. Every time it passed a test, the hull got weaker, and dive 80 is the proof of that. The sub went back down to Titanic depths 2 more times that season, dives 81 and 82, on a hull that had already broken inside. And when the data from dive 80 landed in Stockton Rush's desk, his recorded response was, "Let's dive again and see what happens."
Should be about 500 meters, 30. What was that bag?
Now, we covered in our original video that they had measurement systems in place, like strain gauges to measure this very thing. So why didn't they catch any of this? Because they looked at it wrong. They plotted strain against time, dive by dive, which smears everything together into noise, when investigators took the same exact data and plotted it against depth instead, which makes sense because pressure depends on depth. The failure jumped right off the page. Here's what we can look at. Before dive 80, the whole strain response was a clean straight line at every depth. After dive 80, it went non-linear, but only in shallow water, in the top 500 meters or so, and stayed clean deep down. That's the fingerprint of delamination. Near the surface, the separated layers flap independently, but under deep pressure, they squeeze back together and act like a solid wall again. So the damage literally hides at depth. The Coast Guard replotted that data and said it plainly. The bang, the acoustic spikes, the strain shift were all the same event. After dive 80, the hull wasn't just weaker. It was physically split into loose sheets inside, with gaps between the layers. And the Canadian board flags a nasty property of carbon fiber. It has very low resistance to impact. A knock that steel would shrug off can quietly grow a delamination in composite. So what did OceanGate do with this already cracked hull? Two things that read like a checklist for finishing it off. First, storage. Carbon fiber is supposed to live in a climate-controlled room. The classification experts say 60 to 90 degrees Fahrenheit, under 80% humidity, out of the sun. Instead, the Titan was uncovered in a parking lot in St. John's, Newfoundland, from late July 2022 until February 2023, through a winter averaging around negative 5.5 degrees Celsius, about 22 degrees Fahrenheit. Why does that matter? Well, if water seeps into any of these open delaminations and freezes, it expands like a tiny crowbar, prying the layers further apart. They were quoted about $1,750 for a cover, and they never replied to the email. Second, the tow. Earlier expeditions carried the sub on the ship's deck. In 2023, to save money, they towed it 2,900 miles across the open North Atlantic behind the polar prince. So its already delaminated hull spent thousands of miles soaking up wave impacts, vibration, flexing, and shear, the exact loads that grow cracks. On one dive that season, it slammed against its launch platform for 45 minutes straight. The NTSB is blunt. After dive 82, the hull took additional damage of unknown origin. They can't prove which of the different things we've talked about caused it because that data died with the sub. But freezing water and 2,900 miles of pounding are the named suspects. A already delaminated and shifting hull quietly broke even further, and then they took it to the Titanic one last time. So with all that damage piling up, how did nobody stop it? OceanGate's entire safety pitch rested on real-time monitoring. Microphones bonded to the hull, listening for crackles and breaking fibers so they could hear trouble coming and abort. It sounds clever, but it wouldn't have worked. For starters, 3 of the 8 acoustic sensors were flat out dead through 2022 to 2023. They were flying with a third of the system offline. The system also reset its memory every single dive, throwing away the cumulative history, and any bang on the surface got waved off as docking noise. But there's a deeper problem. Boeing's own engineers testified that buckling the actual way this hull collapses wouldn't necessarily make a sound that the system would catch. The alarm was listening for one thing while the real failure mode might have just completely been ignored. In 2021, those sensors logged 0 concerning acoustic events all season. In 2022, after dive 80, that jumped to 120 per sensor. The hull was audibly coming apart and they kept diving. This is an example of false positives, right? If you have an alarm that goes off all the time, you stop listening to it. That's kind of what happened here. By 2022, it hadn't completely failed yet, but it kept having all these sensors and warnings, and they just figured, this is probably not accurate. Ignore it. It's a classic sign in engineering to make sure that your signals and alert systems don't give you false warnings and don't miss real warnings. And the final irony that Titan's own hull mics never raised the alarm, but a US underwater recorder 1,448 kilometers away, about 900 miles, picked up the implosion roughly 16 minutes later. So, putting this all together, what did the 3 investigations actually teach us? The NTSB's official cause is blunt, an inadequate engineering process, not bad luck, not a freak wave. They never tested a finished hull to failure, only 4 pressure tests total, and they never ran a real fatigue analysis, never did a formal failure mode study, and deliberately operated outside any oversight. Titan was never registered, classified, certified, or inspected by anyone. In 2023, the entire engineering team had shrunk from about 20 people to just 3, with the director of engineering position sitting vacant. Every shortcut was a cost decision, right down to reusing the titanium domes off the first hull that had already failed. Domes once held on by just 4 bolts until one literally fell off during a recovery, and they bumped it to 18. One of the big takeaways with engineering is a lot of what we learn comes from failure. That's why we're doing this video. The reasons why there hasn't been a submersible fatality in decades is that everyone else followed the rules Stockton Rush called wasteful. The Canadian board issued 6 formal recommendations and the rule books tightened. Lloyd's Register updated its submersible rules in 2025, ABS the year before. Now here's the interesting part. Triton Submarines is taking a brand new sub, the Explorer, back to the Titanic this year. But they actually built this right. It's fully certified to DNV standards. The independent board that Stockton Rush mocked as being needless and pointless. Triton already has a sub certified to the deepest point in the entire ocean. So doing this safely was always possible. OceanGate just didn't. Here's an analogy. This is a silicon wafer. On here, you see multiple like chips. These would be like maybe the CPUs in your computer. And this is how they come out. Now, when they come out of the fab, do you think every one of those is perfect? No. What they do next is they'll cut these up into pieces, test them. Some of these will be really good, meaning more of the transistors work. Those will be binned as great CPUs. They'll be the 9900s. Some of them will have some that weren't quite built correctly that don't work. And so they'll detune those and call those Celerons, right? Different lines of chip. They just make one. And because of how impossibly difficult it is to build things at 5 and 7 nanometers, they have variability. Now, the submersible industry is the opposite end. It's large engineering. And building carbon fiber in large quantities is not easy. And it's error prone. Nothing that we build is perfect. You might see a car lot and see 10 cars in a parking lot and think, those cars are identical. They're not identical. Every one of them will have little variations. We call that tolerances, right? Until we get the Star Trek cloning machine that can make exact copies of things, that's just not possible in engineering. There's variability in all things. That's why you have to do testing. The problem that I see here, and I think we have to remember, is building a submersible to take human lives, souls down into the ocean is not the same as like a software startup. We have to be more diligent with how we build things. And I know why they rushed this, because I think Stockton Rush was pretty rich, but not, like Bill Gates rich. And he wanted to be profitable without going too deep into the red. But the thing is, I think you have to build hole 1 and hole 5 and hole 10 and crush them and lose $1 billion before you're profitable 10 years from now. And the only way to do that is to go public and to raise funds. But that's what it takes. You can't build one model and start taking people down over and over without understanding the fatigue. Fatigue is an engineer's worst nightmare. We don't fully understand sometimes, and we can't guarantee. Take the same part, apply the same loads to it until it breaks, and you'll get different variations in the same exact part because the supply of the material, the engineering, the machining, everything is slightly different. So what you do is you over-engineer it. That was that safety factor of 1.25 we talked about. And then you say, okay, at this many hours, you throw it away well before it'll ever fail. That is how you do engineering. And it's really complicated with new things like carbon fiber, which we've only been using for a couple of decades. And fatigue and strain and stress, cracks aren't as well understood. And even the investigative methods like non-destructive investigation techniques are not as well established as traditional steel or titanium or aluminum, for example. The engineer has to follow through to this point. Really, really great people devoted years of their lives to give us this information. And it tells a pretty striking story that engineering due diligence is really important. If you ever hear a story about a company cutting engineers, to me, that's a red flag. Don't cut engineers. There's a lot of ways you can save money, but something like this, that's not a good idea. All right. Now, what do you think? Were there any other things that we missed? If a new submersible was built with really rigorous engineering standards like the Triton maybe, would you take one down to see the Titanic? Sound off in the comments below. That is a rundown of what we've learned, the engineering investigation process for the OceanGate Titan. We'll catch you next week.